to the second lecture for the course Basics of Electrical and Electronics Engineering EST130 Module 6. I am Poornima S, Assistant Professor, Department of Applied Electronics and Instrumentation, Rajagiri School of Engineering and Technology. Today's lecture is on the topic Radio Communication, Principles of Amplitude Modulation and Frequency Modulation. The textbook for your reference is Electronic Communication Systems by George Kennedy. This lecture gives you an understanding of the concept of modulation, different types of modulation, the basic principles of amplitude modulation and frequency modulation, its various applications, advantages and disadvantages, and finally a brief summary. So, what is communication? It is a method of transmission of information from one place to another. The most popular way in which people communicate with each other is through speech. So, what is the frequency range of these speech signals or in general audio signals? The frequency ranges from 15 Hz to 20 kHz. These are low frequency signals. So, can the sound signals travel long distances through air? No. Even sound from a loudspeaker can propagate only over small distances. Another problem is that the amplified sound can get mixed up with sounds from nearby speakers. So, what are our requirements? We need to send an audio signal to far off places and we need to avoid mixing with other audio signals. The solution to this problem is modulation. To understand modulation, you need to be familiar with certain terms. So first, let us consider a periodic signal, say a sine wave. The signal level is plotted on the y-axis and the time is plotted on the x-axis. You can see that the signal level swings to both positive and negative sides from the mean value. The maximum swing from the mean level is called the amplitude of the sine wave, and the time taken to complete one cycle of the wave is called the time period of the wave. The time period can be marked in different ways. It can be marked from one crest of the wave to the other crest, or from one positive to negative zero crossing to the other positive to the negative zero crossing, or from one trough of the wave to the other. The next term is wavelength. Wavelength is the distance traveled by the wave during one time period. The inverse of the time period or the number of cycles in 1 second is called the frequency of the wave. So in general, a sine wave can be represented by the equation V of t is equal to Vm sine 2 pi ft plus phi. Here, V of t is the signal level at any time instant of the wave. Vm is the amplitude of the wave. F is the frequency of the wave. And phi is the phase of the wave, which represents the shift of the wave from a reference point. So let's recollect. The maximum swing from the mean level is called amplitude of the wave. The time needed to complete one cycle of the wave is called time period of the wave. The number of cycles in 1 second or the inverse of the time period is called the frequency of the wave. And phase of the wave is the shift of the waveform from a reference point. So now that you are familiar with the terms amplitude, frequency and phase, we can now define modulation. Modulation is the process by which the amplitude, frequency or phase of the carrier signal is varied in proportion to the amplitude of the message signal. Here, the carrier signal is a high frequency signal which carries the message, which is a low frequency signal. So, the signal to be modulated or the message signal can be called as the modulating signal, and the signal after modulation can be called as the modulated signal. So, the signal to be modulated is called the modulating signal, and the signal after modulation is called modulated signal. Let us consider a simple example to understand the concept of modulation. Alice and Harry are standing on either side of a river and wants to communicate with each other. Even if they shout, they are not able to send their voice across. Alice uses a simple technique. She writes the message on a piece of paper, wraps it around a stone, and throws the message. Harry catches the stone, throws the stone away, and reads the message. In this example, the paper can be compared to the low frequency message signal which is to be communicated. The stone as the high frequency carrier signal which carries the message. The wrapping of paper on stone can be compared to the modulation technique. This picture shows a simple block diagram of modulation. The modulator takes the modulating signal and the carrier signal as inputs to produce the modulated signal as the output. The modulated signal is then given enough power amplification by the power amplifier and transmitted through the antenna to the destination. Now, can modulation satisfy our requirements which we stated earlier? Yes, it allows transmission of information over long distances without interfering with other signals. The distance of transmission can be improved by proper amplification and then transmitting through the antenna. The interference with other signals can be prevented by using different carrier frequencies for different messages. Now, what is the size of the antenna? The size of the antenna is proportional to the wavelength of the signal. We know that wavelength of the signal is inversely proportional to its frequency. Let us take an example. Consider a low frequency audio signal of frequency 3000 Hz. Its wavelength is given by speed of the wave by frequency of the wave. Since the audio signal is an electromagnetic wave, the speed is given by 3 into 10 raised to 8 meter per second. So the wavelength is calculated as 100 kilometers. We know that the size of the antenna is proportional to its wavelength. If we consider a simple monopole antenna, the size of the antenna is given by lambda by 4, which is 25 kilometers. Practically, it is impossible to make an antenna of 25 kilometers long. Now let us consider another frequency which is high. Say f is equal to 100 megahertz. The corresponding wavelength is 3 meters. Now the size of the antenna is calculated as 75 centimeters only. From this example, it is clear that modulation can reduce the size of the antenna by using a high frequency carrier. To summarize, the modulation has several advantages. It helps to improve the range of communication. It avoids mixing between signals. It improves the signal quality and reduces the size of the antenna used for transmission. Now let us look at different types of modulation. In this course, we are looking at mainly two types of modulation: amplitude modulation or AM and frequency modulation or FM. Let us look at amplitude modulation or AM. In amplitude modulation, the amplitude of the carrier signal is varied in proportion to the amplitude of the message signal. Now let us look at the waveform of the amplitude modulated signal. Consider a message signal given by a simple sine wave of low frequency. Now consider another sine wave of high frequency as our carrier signal. As discussed earlier, in AM, the amplitude of the carrier signal is varied in proportion to the amplitude of the message signal. So, in the AM signal, you can clearly see that the amplitude of the message signal is impressed upon the amplitude of the carrier signal. Now let us look at the mathematical expression for AM. If the message signal is represented as m of t equal to am sine 2 pi fm t and the carrier signal is represented as c of t is equal to ac sine 2 pi fct, then the amplitude modulated signal is given by Vam of t is equal to AC plus m of t sine 2 pi fct. This can be expanded as AC plus Am sine 2 pi fmt sine 2 pi fct. Here you can see that the amplitude of the carrier is changing with respect to the amplitude of the message at every instant of time. Now let us look at the effect of modulation on the carrier signal. Consider a low frequency message signal MT and a high frequency signal C of T. If the message signal amplitude AM equal to 0 and the carrier signal amplitude AC equal to 1, the AM signal will be looking like this. You can see that the amplitude of the carrier is not changing because message amplitude equal to 0. Now if AM equal to 1 by 2 and AC equal to 1, how will the AM signal look like? It looks like this. See that the amplitude of the message is added to the amplitude of the carrier signal. Let us consider another case. When AM equal to 1 and AC equal to 1, how will the AM signal look like? It looks like this. See that the amplitude of the AM signal is becoming 0 at certain points. So this is the maximum extent of modulation possible. Now what will happen if AM is greater than AC? The AM signal will look like this. You can see that in certain areas the signal is totally missing. So always remember that for proper modulation, the signal amplitude AM must be less than the carrier amplitude AC. The extent of modulation is decided by a factor called Modulation Index. It is given by the equation m is equal to AM by AC, where AM is the amplitude of the message signal and AC is the amplitude of the carrier signal. M is chosen to be less than 1 for proper modulation. Modulation index can also be calculated from the received AM signal. If this is the received AM signal, let Amax be the maximum amplitude of AM wave and Amin be the minimum value of the AM wave. Then the modulation index is given by Amax minus Amin by Amax plus Amin, where Amax is the maximum amplitude of AM and Amin is the minimum amplitude of AM. What are the applications of AM? AM is used in walkie-talkies. AM can be used in radios, but these days it is less common due to the popularity of FM. Another important application of AM is in air-to-ground communication. The aircraft pilots request the ground station for landing using AM. Another type of modulation is frequency modulation or FM. In frequency modulation, the frequency of the carrier signal is varied in proportion to the amplitude of the message signal. Let us look at the waveforms. Consider a low frequency message signal and a high frequency carrier signal. The frequency modulated signal will be this. Notice that the time period of the FM signal is small when the amplitude of the message signal is high, and the time period of the FM signal is large when the amplitude of the message signal is low. We know that the frequency is inversely proportional to time period. So we can say that the frequency of the FM signal is high when the amplitude of the message signal is high, and the frequency of the FM signal is low when the amplitude of the message signal is low. This is how the message is incorporated in the frequency of the carrier signal. The distortions in amplitude does not affect the message. Hence, FM has better clarity than AM. Let us look at it mathematically. If the message signal is represented as m of t is equal to am sine 2 pi fmt and the carrier signal is represented by c of t is equal to ac sine 2 pi fct, then the instantaneous frequency of the FM signal or the frequency at each instant is given by Fi of t is equal to Fc plus Kf into mt. Here, Fc is the carrier frequency, Kf is a scaling factor having the unit Hertz per volts, and m of t is a message signal. Expanding the m of t, we get equation number 1. See that in the FM signal, the frequency of the carrier signal varies as a scaled version of the message amplitude at different times. We know that the sine 2 pi fmt takes values between -1 and +1. Substituting equation 2 in equation 1, we find that the frequency of FM takes values between Fc minus Kf am and Fc plus Kf am. From this we can say that the difference of frequency of the modulated wave from the carrier wave is Kf am, which is called the frequency deviation of FM, delta. For frequency modulation, the modulation index is given by MF is equal to delta by FM, where FM is the frequency of the message signal. Now, what are the applications of FM? FM is most commonly used in FM radios. It is also used in FM radars, for magnetic tape recording, EEG monitoring of newborns, etc. What is the frequency range of operation of both these modulation schemes? AM typically uses frequencies ranging from 540 to 1600 kHz, supporting around 106 possible bands with 10 kHz or more bandwidth. FM uses frequencies ranging from 88 to 108 MHz, supporting around 100 bands, each having a bandwidth of 200 kHz. Let us now look at the advantages and disadvantages of AM and FM. AM is more prone to noise because information is contained in the amplitude of the signal. Amplitude gets attenuated as it propagates through the medium. FM is less noisy because information is contained in the frequency. So variations in amplitude will not affect the message. AM circuit is simpler than FM. We can get back the message from the AM signal easily from its envelope. A simple circuit called envelope detector is used. The FM circuit design is more complex than AM. Retrieving the message back from the SM signal is not that simple. AM consumes more power than FM. The distance up to which the AM signal can travel depends on the output of the antenna used for transmission. FM consumes less power. In FM, the information is contained in the frequency, hence amplitude attenuations will not affect the information. FM has less coverage. FM makes use of much higher frequencies than AM as the carrier. These high frequencies travel in straight lines and are useful for line of sight transmission. They are limited by the Earth's curvature. The range can be extended by increasing the height of the antenna. In this figure, you can see that the range of the high frequencies are limited by the curvature of the Earth. So they are limited by only line of sight transmission. So to increase the range, we need to increase the height of the antennas used on both sides. AM has larger coverage than FM because AM uses frequencies which propagate along the Earth's surface. In summary, the amplitude modulation is more prone to noise and has lesser clarity. The FM is less prone to noise and has more clarity. AM uses a simple circuit, but FM uses more complex circuit. AM consumes more power for transmission, whereas FM consumes less power. AM has larger coverage, whereas FM has less coverage than AM. Thank you.